Hello my dear students, welcome to our channel MS2 Physics where physics gets charged. So in the today's video we are going to start the moving charges and magnetism from 12th standard. So in this especially we are discussed about the magnetic effects of current. Previously in the electrostatics we already discussed the number of topics, right? So in that we have discussed that whenever we are taking one charged particle and placed it anywhere, it produces the electric field around it, whether it is at rest or in motion. And due to that electric field we are discussing the number of topics and different applications there. But here now when the charged particle is in motion, then what happens, right? So here, so in the electrostatics we know that whenever we are taking one charged particle of charge q, around it affecting some region, the region up to where the effect of this charge is present is known as a electric field. We already discussed this. Now in this especially moving charges means when this charge is set into motion with a certain velocity. So here this moving charge around it not only produce the electric field and it also produce the magnetic field here. This is what first observed by Oersted. This is what first observed by Oersted in 1820. So this magnetic effects of current because this moving charges are said to be current only, right? So this current carrying conductor is producing the magnetic field around it, and this moving charge also produces the magnetic field around it. Was first observed by Oersted in 1820. Okay, that is what they are taking one experimental arrangement, that is magnetic needle of north south is placing near to the one current carrying conductor, so that he observed that whenever the current flows through this wire, so that only this magnetic needle get deflects, and when this is switch off means when no current is flowing through this, no deflections are observed in this magnetic needle. So basically we know that whenever we are taking the magnetic needle and that magnetic needle is placed at nearby any magnet, so that only it get deflects either in clockwise or anti-clockwise, depends on the polarity of the poles of magnet as well as the magnetic needle, isn't it? But here without any magnetic bar magnet or magnetic material, so only because of this current only the magnetic will deflects. By this he understood that yes, there is some generation of magnetic field around it when there is a current passing through it. And he also observed that when he changing the direction of current means now the current is towards left side, so that the north pole of this magnetic needle get repelling from it, which means the south is attracting towards it. Here north is attracting towards it, so which means the south will be repelling from it. Means he also conclude that whenever there is a change in direction of current, there should be a change in the direction of magnetic field. When there is a change in direction of magnetic field, so that only there should be a change in direction of the deflection of the magnetic needle. This is what first observed by Oersted here. Then again the point is, sir, you said that when there is a change in direction of current, there should be a change in direction of magnetic field. Okay, then how we could find that produced magnetic field direction, sir? So that to know this direction of the generating magnetic field either due to motion of charged particle or this current carrying conductor, okay, we have some rules here like a right hand thumb rule, Maxwell corkscrew rule and Ampere's rule, and number of such rules are there. So let me take the basic rule is the right hand thumb rule. So by using this rule we can find the direction of generating magnetic field because of current flows through any current carrying conductor. So according to him, whenever we are stretching our right hand in such a way, so we are holding this current carrying conductor in palm of our right hand, so that whenever we are holding this current carrying conductor, the thumbprint is supposed to be in the direction of current carrying conductor. So in order to holding it, we need to curling the fingers. Without curling the fingers, does it possible to hold it? No. Means now when this thumb is gives the direction of current, then the curling fingers, the tip of the curling fingers is gives the direction of generating magnetic field. And if you are observing this phenomena, these curling fingers are around the conductor, which means he also concluded the next thing is that because of any current carrying conductor, magnetic field is generates, and that generated magnetic lines of force are around the conductor in a closed loop. And if you are observing again, my thumbprint is in the direction of current. This plane of the magnetic field which is generates is perpendicular to the direction of current, or perpendicular to the direction of a current carrying conductor, which means the passage of current in any wire is producing the magnetic field, and that produced magnetic field is around a conductor and normal to the plane in which the conductor is present. These all are the important conclusions about this right hand thumb rule here. And similarly, we have one more Maxwell corkscrew rule. So this Maxwell corkscrew rule stating that, so we know basically, you know the about screw here. The spiral arrangement of screw, and at last we have one tip here, isn't it? So whenever, otherwise we are taking this only, this is the tip of the screw here, and in order to advancing into the wall here, we need to rotate it in a clockwise direction. It goes inside, and whenever you are rotating in an anti-clockwise direction, so that it comes outside. Means now, according to Maxwell corkscrew rule, when tip of the screw is advancing in the direction of current, then the rotation of this curves either in clockwise or anti-clockwise gives the direction of magnetic field. If you are observing here, when you are advancing this, I am rotating here in a clockwise so that it goes inside. When the current goes inside, the current magnetic field is in clockwise. When I am taking outside, which means current is away from the plane of the paper, the direction of generating magnetic field is outward. In both the cases, if you are observing here, this rotation is a closed loop, and these loops which are formed by the generated magnetic fields are normal to the plane in which the conductor flows, in which the current flows in the conductor here. This is the way the Maxwell and right hand rules are giving the direction of generating magnetic field here. And here in this throughout chapter, the generated magnetic fields either into the plane of the papers or away from the plane of the papers, are clockwise or anti-clockwise, so that the generating magnetic field are inward. So it is the symbol of the meaning of this symbol is into the plane of the paper or plane of the board, everywhere please, and this dot indicating that away from the plane of the paper, away from the plane of the paper or plane of the board where we are placing the conductor. And these two directions we are using either for magnetic field or for current or for the velocity of the charged particle. So why? Because whenever you know the direction of current, so that only you can know the direction of generating magnetic field. Okay, without knowing the direction of current, can you specify the direction of producing magnetic field? Of course, we know that because of flow of current through the conductor, the magnetic field is generated, fine. But can you predict the direction of magnetic field without knowing the direction of current? No, it is not possible. So that here either inverse or how it is I am showing now. So how it is we are using this? By knowing the direction of current only, we can know the direction of generating magnetic field. By knowing the velocity of the charged particle only, we can know the direction of again generating magnetic fields. Now we will take some examples to know the direction of generating magnetic field either by this right hand thumb rule or this Maxwell corkscrew rule. Now we are taking a straight conductor which carries the current towards right. It is in the plane of the board. So now my intention is to know the direction of generating magnetic field at a point P and at a point Q. Okay, otherwise if you are taking the same current carrying conductor but which carries the current in a leftward direction opposite to the initial ones. So here again, above the conductor, below the conductor, we are going to know the direction of magnetic fields, right? So in this, so when the conductor is given, so at first you should stretch your thumb finger. You should stretch your thumb finger is in the direction of current, is in the direction of current, so that, okay, so you need the magnetic field at a point P. So when you are stretching your thumbprint in the direction of current, your pointing finger, your tip of the fingers comes outside, means here above the conductor magnetic field is away from the plane of the board, and at a point Q this tip of the fingers goes inside, which means here we can give the direction of magnetic field B by inward. Here, sorry, it is outward, and here it is inward. Once again, see here, I am stretching the thumbprint is in the direction of current, so that my tip of the fingers comes away from the plane of the board, and these fingers goes inside below the conductor. Means here you should check the direction of the tip of the fingers with respect to the point where we are going to find the direction of magnetic field, please. Say for the same conductor, above is away, below is inside, which means when it is coming away from it, goes inside. It is a 3D picture. This again goes inside, means the spirals like loops are formed of magnetic field lines. So when coming to here, okay, so now I am stretching this thumbprint is towards left, so that above the conductor my tip of the fingers goes inside, means here the direction of generating magnetic field is into the plane of the board, so that below the conductor my fingers comes out, so that here we can give this is what the direction of generating magnetic field above the conductor, here it is away the conductor, below it, inward and outward. These two are in the horizontal direction. So sir, if you are taking they are in the vertical direction, sir, means in the plane of the board only, again in the plane of the board only. In a one the current is upward, the current is downwards. These two are the currents here, current carrying conductors. So now to the right of the conductor and to the left of the conductor, my intention is to know the direction of generating magnetic field. Yes, once you check yourself, so stop the video and check yourself. So stretch the thumbprint upwards, and I need the magnetic field at right of the conductor. So at right of the conductor my tip of the fingers goes inside, and to the left of the conductor my tip of the fingers are coming outside, so that I conclude that at right of the conductor magnetic field is inward, and to the left of the conductor the magnetic field is outward. Similarly, when I am coming to here, now the current conductor is in the vertical plane only, in the plane of the board, but now the current direction is downward, so that I am stretching my thumbprint in the downward direction. After stretching the downward direction, if your intention is to know the direction of magnetic field here, so that the tip of the fingers away from the plane of the board, normal to the plane of the board, please, and now this tip of the fingers goes inside. When they goes inside, so that here to the left of this conductor magnetic field is inward, and here it is outward. This is the way we can find the direction of magnetic field by using right hand thumb rule. Okay, for the conductor which is in the plane of the board, either horizontal or vertical. The same thing you can use now, say the screw rule. So for the screw rule here I am taking this one. So this is the tip of the screw, and it is advancing upwards. Now to advancing upwards I am rotating in a clockwise. When it is a clockwise, see this caliber goes this side, means inside, and coming out from left of the conductor, means it is inward and it is outward, means whatever the rule you may take, the direction will not changes. The way the what's called the mode of specification of the direction is changes, but the direction of resultant magnetic field won't be changes. So I am rotating in upwards. So now it is in a clockwise again. When this side, why? Because now the tip of the screw is downwards. When I am rotating here, I am rotating in an anti-clockwise. So goes inside, come outside, goes inside, come outside. This is the way we can find the magnetic field direction for straight conductor. Now I am coming to know for circular current carrying conductor. Sir, this is the circular current carrying conductor, and later in this the current is supposed to be in a clockwise direction. Current is in a clockwise direction. So or you may take another example is that again it is a circular current carrying conductor, but the current is anti-clockwise direction. So now our intention is to find the producing magnetic field at the center of the conductor, which means again we need to stretch the thumb in the direction of current, so that say here now I am stretching the thumbprint in the direction of current. So tip of the fingers or goes inside, not only here when it is said to be clockwise. So this is the way we will take. Here it is anti-clockwise. So wherever you may take. See, here I am taking now. See, this is anti-clockwise. My tip of the fingers comes outside. Here, when you are taking with respect to this direction, this is the current direction. Outside, outside. Here, inside, inside, inside. Means here the direction of producing magnetic field at the center is inward, and here it is outward. This inward into is indicating inward, and this dot is indicating away from the plane of the board. This is the way we can find the direction of generating magnetic field. Just stretch the thumbprint in the direction of current. See where the tip of the finger goes, inside or outside? Inside. When you are coming to here, I am just stretching the thumbprint in the direction of current, so that automatically the thumbprints are coming outside. Means no need to adjusting this curling fingers, please. Just you stretch this thumbprint in the direction of current and trying to form the closed loops. During the formation of these closed loops, automatically this tip of the finger showing that whether they comes outside or goes inside. This is the way we can find the direction of generating magnetic field. Otherwise, if you are taking the current carrying conductor is into the plane of the board like this, means it is the 3D now. Now these all things 1, 2, 3, 4, 5, 6 all are in the plane of the board. So now what I am taking here is normal to the plane of the board, means this is the current carrying conductor now. When this is the current carrying conductor, so automatically around it magnetic field is generates or not? When it is around it, magnetic field generates. To know the direction of magnetic field, whether it is a clockwise or anti-clockwise, why? Because you take the two conductors here, one is into the plane of the board, another is away from the plane of the board. Okay, so first I am taking this. When I am taking this here, when the current is inside, stretch the thumbprint is into the plane of the board. So now if you are stretching your curling fingers, it shows what? Clockwise, means in this direction. Around it magnetic field will be produced here. So now check yourself this one. Yes, come on. So now the current is away from the plane of the board, means stretch the thumbprint away from the plane of the board, then again trying to forming the loop. So your tip of the fingers now showing in an anti-clockwise direction, so that here again the magnetic field is generated. That generated magnetic field is out, what's called in an anti-clockwise direction. This is the way we can find the direction of generating magnetic field, whether the current carrying conductor is a straight end in the plane of the board, vertical in the plane of the board. Okay, these are the circular loops or current carrying conductors. Now here the straight conductors, but these conductors are, one is inward, another is outward. So this is the way we can find the direction of generating magnetic field. Thank you for watching. If you like my videos, do like, share, comment and subscribe my channel to get more videos.